Good morning, everyone. The presentation deals with exploring the cost optimal of motor traffic street lighting infrastructure over a 20-year period of time. And the first result of our study is not really related to buildings, but it's very close to energy and sustainability in the urban environment and urban infrastructures. You can also see there's a poster at the back later on related to this presentation. Sorry, it's not working.
You can use the...
Okay. Mr. Haralambopoulos presented me, so it's, I will move forward. There is an ongoing research on optimization techniques towards energy efficiency, energy management, sustainable and environmental friendly street lighting systems, along with the avoidance of light pollution and, of course, users' well-being. Of course, actions need towards a more sustainable environment, follow the use of new lighting equipment and along with the latest management systems, selecting the most sustainable solution in light tenders, and also the cost optimal solutions over a 20-year period, which is the topic of this presentation as well. A bit of, municipalities and regions in Greece have started the last 5 to 8 years to renovate their street lighting infrastructures. Unfortunately, lighting tenders are limited at meeting lighting design criteria proposed by the standard EN 13201-2, which is performance requirements, focusing only on luminance uniformity, the threshold increment, and the edge of luminance ratio, and also some financial issues and the energy that needs to be achieved according to the tender. Unfortunately, they take no consideration of environmental criteria, energy performance indicators, or adaptive lighting that are also presented by the standard. Research up to now has shown that a good combination of parameters can achieve higher saving rates. There are a lot of parameters that are related to road lighting design, and these have to do with design parameters, on-site elements, or equipment and technology parameters. As we can see on these specific graphs, we can see that a lot of energy can be additionally saved if certain parameters have been taken into consideration. So we can have like 15% more energy saved, or up to 30% additional more energy saved. Also, when smart systems or electronic ballast and microcontrollers and things like that, like technology equipment, are being used in road lighting installations, can achieve much more energy saved and sometimes up to 90% in certain cases. Also, evaluation between companies is very crucial for the optimal energy outcome, especially when the unit is applied. Past research that we have done like a couple of years ago on a light tender between two different companies, LED 1 and LED 2, has, with the same wattage and lumen output, has shown that when dimming is applied, the two companies act very differently in, compared to their consumed power. So we could have, we can see that we have additional saving in certain cases compared to other cases. So this, when dimming is applied, it's very important to evaluate more the companies that take part in the tender. The improvement of the road lighting sustainability includes a large number of parameters, such as luminaire characteristics, luminaire type, lamp type, power consumption, light intensity, light distribution, and luminous efficacy. Lighting design characteristics like luminance, uniformity that we have mentioned earlier, the threshold increment and the edge of luminance ratio, and of course the lighting class that characterizes every street. Also road characteristics like pole spacing, pole heights, and road width, along with environmental issues like the correlated color temperature of warm white like 300 Kelvin, the use of full cutoff luminaires, luminaire inclination at 0%, and ULOR at 0 degrees. Along with the user's well-being, which is glare, correlated color temperature, and uniformity. All these parameters have been used in order to achieve, to study the cost-optimal solution that is divided in the purchase and installation cost of the equipment that is being used in road lighting installation, meaning the poles, the arms, and the luminaires, and also the operation cost of the system over 20 years, over a 20-year period. This graph shows the methodology that can be used in order to select the most cost-optimal solution that will be analyzed in the following slides. A case study has been used with a two-lane motor traffic road, which is the most typical street lighting type in Greece. We can meet these type of streets in national roads and major streets in municipalities. Also, 4 different pole heights have been evaluated, pole heights between 9 meters and 12 meters that are usually met in this kind of infrastructures, and also 12 different, same fitting with 12 different light distributions was evaluated in order to see the best lens for this specific road lighting situation. One more thing to mention, a very important parameter, is the pole distance that plays a crucial role in road lighting infrastructures because it indicates the number of poles that will be used per kilometer according to the cost, compared to the cost that is necessary for the installation of, for the creation of this infrastructure and its function. Certain calculations have been evaluated on road lighting software. 2 groups of luminaires have been tested. One group is with same power and same luminous flux used in all cases, and the second group of calculations used the optimization power and optimization luminous flux of the fittings in order to achieve the optimal results of each study. All cases firstly achieved lighting design criteria proposed by the standards, that was the luminance uniformity, TI, and the edge of luminance ratio, which is the ambient lighting of the street. If we calculate the 12 different lenses and multiply with the 4 different pole heights and the group 1 and group 2 types of calculations, we get a total number of 96 simulations. The evaluation focused on the purchase and installation cost and the operating cost over a 20-year period of time, and the total cost, which is 1 and 2 in addition, in order to achieve the cost-optimal solution. A bit of background information. Analytical process for electrical and mechanical works, which is a Greek legislation 1746-2017, has been used in order to get certain prices for the luminaires in certain wattages. and also the poles, the cost of the poles in certain heights. Also, the kilowatt-hour price was considered as 0.1502 according to the special tariff for lighting of squares and streets. We call it FOB in Greek. And the operating hours has been considered according to Athens Greek meteorological year as 4,086 hours operating per year. The results, interesting results, have come out from this methodology. We have the graphs present the purchase and installation cost compared to different the pole distance achieved for 4 different pole heights. Also the operation cost for 20 years compared to the pole distance achieved for the 4 different pole heights. And the total cost compared to the pole distance achieved for the 4 different pole heights. Results have shown that purchase and installation cost in all cases is the most important expense, constituting the largest percentage of the total cost, about 70%. As pole height increases, as we can see on the graph, purchase and installation cost decreases as the number of poles and luminaires per kilometer decreases accordingly. On the other hand, the operating cost slightly increases as pole height increases and hence energy consumption. As pole height increases, maximum pole distance achieved is also increased. And we can see on the table that at 9 meters high, the average pole distance achieved is 39.7 meters, while at 12 meters high, we have 48.5 meters high, meaning that we have less poles and luminaires used per kilometer. The average total cost for 20 years seems to get higher as pole heights increase. In these graphs, we can also see some comparison between the different pole heights in the same situations, comparing the results using the same watts of luminaires and the optimization results. We have that we can see that at 9 meters high, we have kind of similar results between the group 1 and group 2 that we mentioned earlier. Calculations, while when the pole height is getting higher, the results start to get much different. And at 12 meters high, we have much more higher pole distances achieved in optimization calculations. Now a bit. Some results regarding optimization group 2. As pole distance, the graph shows that as pole distance increases, as pole height increases, maximum pole distance achieved is also increased. The average purchase and installation cost decreases, as we can see here. The average purchase and installation cost decreases as pole height increases. While the operation cost over 20 years increases as pole height increases, and the average total cost for 20 years decreases, compared to the other case that we mentioned earlier, that average total cost was increasing as pole height was increasing. This graph also shows that this type of luminaires that a bit diverge from the graph, from the total results, so that these lenses might not be correct for this specific situation. And also this the red circle shows that the best lenses for this specific road lighting situation, because they get the maximum pole distance achieved, and also the lowest total cost of the installation over 20 years of time. Here we present the cost optimal results. see that as pole height increases, the power consumption of luminaires also increases. The pole distance achieved increases, and the purchase and installation cost decreases, while operation cost over 20 years increases. Here the total cost slightly increases, but in a very much small percent, like 1 to 3%. And also we can see that the best length for this specific situation is length G, that we can meet in most situations, apart from pole height at 12 meters high, that we have another result, additional result, because of the height of the luminaire. But also length G is also an optimal result if we want to use the same fitting for all situations. Here we have the conclusions that we mentioned earlier. And however, the total cost increases, but in very small percent we mentioned. However, if maintenance cost is also considered, it is definitely advantageous to have fewer poles and luminaires to maintain in large road lighting infrastructure compared to compared to fittings with lower wattages. Also, optimization studies have shown that although luminaire power is increased, the total cost of the lighting infrastructure is less compared to all study results. And of course, less poles and luminaires are being used per kilometer. Just to sum up a bit, European technical report from 2019 states that European illuminated streets occupy more than 1.5 million kilometers and have installed more than 64 million luminaires. And maybe this is more today, 5 years later, constituting 1.6% of the European total electricity consumption and 1% of global electricity consumption. Therefore, we can see the enormous operating expenses for the authorities, and so many actions need to be taken into consideration. Any action towards energy efficiency is necessary. Roads should be designed and operated at minimum cost. Light tenders should select cost-optimal solutions, while at the same time ensuring visual comfort and users' well-being. Thank you very much for your attention. If you have any questions, please feel free to ask.
Thank you.